Good afternoon, it's Professor Shannon Gracie. Today we'll be covering how to find the real zeros of a polynomial function. You can go ahead and read our goals listed below. And we will be using the Sullivan and Sullivan text, Precalculus enhanced with graphing utilities. So here we go. Are you ready? Let's go ahead and start off with the warm-up. We'll be dividing a lot this time. So go ahead and divide. You probably learned polynomial long division and synthetic division in intermediate algebra. So if you remember, pause the movie and warm it on up. If not, just follow along with me. All right, so there's two ways you could go about this. You could use polynomial long division. Or you could use synthetic division. So I'll show both ways. Synthetic division only works if you have a divisor in the form of, so divisor in the form of x minus c. Polynomial long division you can use with any type of divisor. So here we go. So polynomial long division, we are dividing, our divisor is quantity x minus 1, so you might want to put parentheses around that. And then the dividend is x squared minus x plus 1. So if I go through and I'll get, I'm looking for x times what number is x squared. So the answer to that is x. And then you have to distribute that x throughout the divisor x minus 1. So you'll be getting x squared minus x, and then you're going to subtract that whole quantity. So the minus sign will distribute to both of those terms. And then what happens is, do you see both of them zero out? So you'd bring down this plus 1, and that is your remainder. So we would get x, and then plus 1 over x minus 1 is the remainder. Now, using synthetic division, so x minus c, so we have our c is equal to x minus c is x minus 1. So that means c is equal to 1. If there had been a plus sign there, c would have been a negative number. So you put the 1 in the box, and then you just put the coefficients of the terms in. So it'd be 1, negative 1, and 1. Leave space for another row, and then what goes in that right box there will be the remainder. So when we bring this 1 down, remember that you go across. So 1 times 1 is 1, so you put it into the next column. Negative 1 plus 1 is 0. So then you do 0 times 1 is 0. Whoops, I'll do this one. Is 0. And then 1 plus 0 is 1. So with synthetic division, since you divided by a binomial that has a degree of 1, that means that you decrease the degree in the dividend by 1 for your answer. So that means that this is 1 times x plus 0 plus 1 over x minus 1, which of course is x plus 1 over x minus 1. So whichever way you slice it, the result here is x plus 1 over x minus 1. Now, let's go ahead and take a look at what we'll be using this for. So as we had said, the numerator of this expression was the good dividend, and the denominator was the divisor, and our result had a remainder, or a quotient plus a remainder in x. So it turns out that if f at x and g at x denote polynomial functions, and if g at x is a polynomial function whose degree is greater than 0, then there are unique polynomial functions q of x and r of x such that f at x divided by g at x is equal to our quotient in x plus a remainder in x divided by the divisor, which was g at x. Now another format that you could write that in is if you multiplied everything through by g at x, you would have an equivalent format that said, or that reads, f at x is q at x times g at x, and then plus our remainder in x. So just depending on the format that one needs, we get either format. So r at x is either the 0 polynomial or a polynomial function of degree less than that of g of x. So let's consider our problem from before. So our warm-up problem was x squared minus x plus 1 divided by x minus 1. And what we got, if you recall, was x plus 1 over x minus 1. Now equivalently, if you multiplied both sides by x minus 1, you would get x squared minus x plus 1 would be equal to x times x minus 1 plus 1. So let's identify, what piece these are. So the f at x was the original numerator. So that was x squared minus x plus 1. G at x is the divisor, which was x minus 1. Now what do you think q of x was? Good. Q of x was x. And then we already have the g of x, so now r at x ended up just being 1. We'll highlight these things. So we have our f at x and g of x were the originals. The quotient in x was the x. So here it's in either one of these formats. And then the remainder in x was 1. So this format here was f at x divided by g at x is equal to the quotient in x plus our remainder in x divided by g of x. This one is set up as f at x is equal to the quotient in x times the divisor g of x plus the remainder in x. And we had said the remainder in x was 1. And we had said the quotient in x was x. Okay? Very good. All right. So let's play around a little bit. Let's see what would happen if we evaluated the original function at the c in the x minus c from the synthetic division. So now consider x minus c, which remember was equal to x minus 1. So c is 1. And let's evaluate f at c, which will be f at 1. And f at 1 is, the original f, member, was x squared, so it'd be 1 squared minus x, so minus 1, and then plus 1. So I'll write it like this. I'll just keep it as f at c. So we ended up getting 1 squared minus 1 plus 1, so f at c was equal to 1. And what was 1? Good, that was the remainder in x. Isn't that cool? So it turns out that you get a whole theorem from this called the remainder theorem. So if f is a polynomial function and it is divided by x minus c, then the remainder is equivalent to f at c. So you don't have to do the whole division problem to figure out what the remainder will be. So it's kind of a cool little theorem. So let's take a look. So in this case, x minus c is x minus 9. So do you see that c is 9? So evaluating f at 9, we will get 2 times 9 to the 4th minus 8 times 9 cubed minus 10. F at 9 is, so let's grab our graphing calculator. So let's see, we had 2 times 9 raised to the 4th minus 8 times 9 raised to the 3rd minus 10 is equal to 7,280. So R of x is 7,280. That's the remainder when you divide by x minus 9. All right, so why don't you try part B on your own, all right, and see how you do. Go ahead and pause the movie and give part B a try. Okay, let's see how you did. Remember, this is equivalent to x minus negative 1. We have to get it in that format of x minus c. So that means that our c is negative 1. So the function evaluated at negative 1 is 2 times negative 1 to the 4th minus 8 times negative 1 cubed minus 10. So f at negative 1 is positive 2, and then negative 8 times negative 1 is plus 8 minus 10. So f at negative 1, do you see, is 0. So what does that mean? The remainder in x is 0 when you divide that by x plus 1. So what do you think about x plus 1? Exactly. So x plus 1 must be a factor of 2x to the 4th minus 8x cubed minus 10. Since it divides n evenly without a remainder. Okay, so that brings us, you guessed it, to the factor theorem. So let f be a polynomial function. So x minus c will be a factor of f if and only if f at c equals 0. So when you have an if and only if statement in math, it goes both directions. So that means if f at c is 0, then x minus c is a factor of f at x. And if x minus c is a factor of, actually, we have a typo here. Let's cross this out. If x minus c is a factor of f at x, then f at c must be equal to 0. So we'll just do a quick little proof about this. So first off, let's take a look at the first statement. So for the first statement, we're going to let f at c equal to 0. So remember from that second version up here, we're going to look at this whoops, went too far. We're going to look at this statement here. F at x is equal to q at x times g at x plus r at x. So we'll come down here and use that. So f at x equal to q at x times g at x plus r at x is f at x equal to q at x times g at x plus 0, because we have a 0 remainder. This gives us f at x equal to q at x times g at x. And that proves it, because that tells us that g at x, the divisor, is a factor. So now going the other way, let x minus c be a factor of f at x. Then there exists some quotient q of x such that f at x is equal to q at x times x minus c. So at x equal to c, we have f at c equals to q at c times c minus c. So I'm evaluating the f from that prior line at x equal to c. So this gives us f at c is equal to q at c times 0, and we have f at c equal to 0, which is what we were looking to show. All right, so there we go. A nice little math proof to brighten up your day. Okay, so let's use this factor theorem to determine whether or not the function given has the given factors. So f at x is 3x cubed minus 6x squared plus 4x minus 8. And the first factor we're considering is x plus 1. So in x plus 1, do you see that this is equal to x minus negative 1, getting it in the right format, which tells us that c is equal to negative 1. So evaluating f at c, which is negative 1, we would have 3 times negative 1 cubed minus 6 times negative 1 squared plus 4 times negative 1 minus 8. So f at negative 1 will be negative 3 minus 6 minus 4 minus 8. So f at negative 1 is negative, what, 21? Does that look right? And negative 21 is not equal to 0. So x plus 1 is not a factor of 3x cubed minus 6x squared plus 4x minus 8. Since we did not get a 0 remainder. Okay, so on this one, c is equal to 2. So f at 2 is 3 times 2 cubed minus 6 times 2 squared plus 4 times 2 minus 8. So f at 2 will be 2 cubed is 8, so we'll get positive 24. Minus, let's see, 2 squared is 4, 6 times 4 is 24, plus 8 minus 8. So f at 2 is 0. So this one works. So x minus 2 is a factor of f at x. And f of x was 3x cubed minus 6x squared plus 4x minus 8. So that means that we could divide 3x cubed minus 6x squared plus 4x minus 8 by x minus 2, and we would get another factor, so we could write f of x as what's called in depressed form, as a depressed polynomial. So using, remember that zero product property? If you can factor these polynomials into linear and irreducible quadratic factors, you can find the zeros of these high degree polynomials. Okay, I'm getting ahead of myself though. A polynomial function cannot have more real zeros than its degree. So if you have a cubic function, you would have at most 3 real zeros, right? If you have a polynomial function of degree 12, you could have at most 12 real zeros. So the rational zeros theorem helps us to find those, right? So f is a polynomial function of degree 1 or higher in this format, where each coefficient is an integer. They have to be integers. So if p over q in lowest terms is a rational zero of f, then p must be a factor of a0 of the constant term, and q must be a factor of the leading coefficient, which is a sub n. So example 3 is asking us to determine the maximum number of real zeros and list the potential rational zeros of this function f. So 1, the max number of real zeros is good, 4, since the degree of this polynomial is 4. Now, secondly, the potential rational zeros, let's find them. So possibilities for p are going to be, so remember, p has to be a factor of the constant term, which is negative 10. So the factors of negative 10 are plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. The possibilities for q R. So Q has to be a factor of the leading coefficient, which is -2. So I'll just write this here. A0 was -10, and A sub n was -2. So we'll just have plus or minus 1 and plus or minus 2 for the possibilities for Q. So possibilities for P divided by Q without repeating any factors would be, so let's go through and start with all the possibilities for P divided by plus or minus 1 will give us plus or minus 1, plus or minus 2, plus or minus 5, and plus or minus 10. Now if I go through and divide all the possibilities for P by plus or minus 2 for Q, what'll happen is the only new one I think I get a couple new ones. So plus or minus 1 over plus or minus 2 is plus or minus a half. Plus or minus 2 over plus or minus 2 gives me plus or minus 1, so I don't need to repeat that. But then 5, right, will get plus or minus 5 halves. And 10 is already covered because plus or minus 10 divided by plus or minus 2 is plus or minus 5, which we already have. Okay? So the number of possible potential rational zeros of this function, we end up with 2, 4, 6, 8, 10, 12 possibilities. And they won't all work because the maximum number of real zeros is 4. So this was part of the answer right here, and then this was the other part of the answer. Okay? All right, so let's do this. This one here, it's another example of that. I actually had the wrong. This is not an equation. I had the wrong directions. The directions are the same as example 3. Example 3. So we're going to determine the maximum number of real zeros and list the potential rational zeros of f at x. Okay? So again, we have all integer coefficients. So a sub 0 this time is 2, and a sub n is 6. So let's see. What are the max number of zeros? Max number of real zeros is good, is 4 because we have a 4th degree polynomial. And then, okay, possibilities for P are, don't be tricked, P, that member is a factor of the constant term. So plus or minus 1 and plus or minus 2 are the possibilities for P. Possibilities for Q are, so 6 is, Q has to be a factor of 6. So plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So the possibilities for P over Q will be, so we'll put the 1 through first, and we'll get plus or minus 1, and we'll divide through by all the possibilities for Q, plus or minus a half, plus or minus a third, and plus or minus 1/6. And then when we divide the possibilities for Q divide the plus or minus 2 by the possibilities for q, we'll have plus or minus 2. We already have plus or minus 1, and then plus or minus 2/3, and then plus or minus 2/6 is the same as plus or minus 1/3, so we're good. So let's see, that gave us 2, 4, 6, 8, 10, 12 possibilities for P over Q. And again, there's more possibilities than there are real zeros, so they won't all work. Okay? All right, so let's go back up here to the box, and this is what summary steps for finding the real zeros. So use the degree of the polynomial function to determine the max number of real zeros. If the polynomial function has integer coefficients, use the rational zeros theorem to identify those rational numbers that potentially can be zeros. And then graph the polynomial function. At this point in the game, you're going to have to use some technology, and that'll give you the best possibility to pick to divide the function by. Then use the factor theorem to determine if the potential rational zero is a factor. If it is, use sympathetic division or long division to factor the polynomial function. So you'll use the division, you'll find a factor, and you'll rewrite your original function. Each time that a zero, and thus a factor, is found, repeat step 4 on the depressed equation. In attempting to find the zeros, don't forget about the factoring techniques that you already know how to do, okay? Okay, so every polynomial function with real coefficients can be factored into a product first uniquely factored into a product of linear factors and or irreducible quadratic factors. And we have all kinds of ways that we can figure out how to find the zeros of quadratic equations. So this is, or the zeros of quadratic functions. So it's good to have linear and quadratic factors. Okay, a polynomial with real coefficients of odd degree has at least one real zero. At least one real zero, because it'll have to cross the x-axis. Okay, so sorry to skip around on you, but before we do an example to deal with bounds, let's go to the first part of example 7 and do an example of how to do what we just learned. Okay, so we're going to find the real zeros of this function, and then we're going to use the real zeros to factor function f. All right, so take a look at it. In the format it's in, could you use factoring by grouping or one of your techniques? I'm looking at this and it doesn't look promising. So we start with our steps. So 1, the max number of real zeros is 3 because it has degree 3. So secondly, we're going to find all the possibilities for P over Q, right? So possibilities for P are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, and then plus or minus 10, and plus or minus 20. And the possibilities for Q are plus or minus 1. So the possibilities for P over Q are just going to be the same as the possibilities for P since you're dividing by plus or minus 1. Okay, so here we go. We found all those possibilities. The third step is to graph. So we're going to go ahead and we're going to get the graphing calculator. And we're going to go and graph this guy. So it was x cubed plus 8x squared plus 11x minus 20 and we graph. Actually, not a bad window here, surprisingly. Let's see what I have for my window. Let's go down. It looks like we weren't seeing the whole picture of the graph, so let's go down to, I don't know, negative 50. See what happens. Now, the only problem here is, I mean, this gives us enough information to actually divide this problem because I see it looks like x is 1 will work out possibly. Although, or no, you know what? My window goes to plus or minus 6. So 1, 2, 3, 4, 5, 6. Yeah, maybe 1 would work. Another potential would be 1, 2, 3, negative 4 might work. But you know, I should increase my window for the x because remember I went to plus or minus 20. So if let me just be more complete than this. There we go. Okay, so I'm looking at the graph. I think I'm going to stick with negative 4. I'm going to see what happens with negative 4. So, I'll paste that graph so we have it. Okay, so the scale was on x was negative 20 to 20, and this is f at x, and this went to 100, and we had negative 50. So let's see, I'm going to try at x equal to negative 4, I'm going to see if that works. So we had seen that when it was more close. So I'm going to try that one, where this is a potential 0, this negative 4 here. So the way we do that is we divide. So we have, so step 4, my c is negative 4. And then if you look at the coefficients, right, of our function, it'll be 1, 8, 11, and negative 20. And then bringing the 1 down, 1 times negative 4 is negative 4. 4 times negative 4 is negative 16, which would give us what? Negative 5. Negative 5 times negative 4 is positive 20. So I got a 0 remainder. So that means that x minus negative 4, or x plus 4, is a factor of the original. And remember that this ends up giving us, we decrease it by 1. So we'll get 1x squared plus 4x minus 5 is what that translates to. So let's see if we can completely factor now. So what we found out is f at x equal to, so the original was x cubed plus 8x squared plus 11x minus 20. And we just found out that we can rewrite it as x plus 4, because our 0 is negative 4, times, and let's see what we got for the division, x squared plus 4x minus 5. And that is something, minus 4x plus 4x minus 5. And that is something that you know how to factor, right? So we'll have x plus 4 going along. The factorization of x squared plus 4x minus 5 is, we'll have an x plus 5 and an x minus 1. That gives us the negative 5 as the product and the positive 4x for our middle term. Okay. So, as you see, the real zeros are at, so the real zeros are when x plus 4 is 0, or x plus 5 is 0, or x minus 1 is 0. So we would get x is negative 4, which we already used, x is negative 5, which is one of the possibilities here, or x is positive 1, which is another possibility. So these are the real zeros. Negative 5, negative 4, and 1 are the real zeros. And this is the factored form. It's fully factored. Okay? Awesome. All right. So, all right, factored form. Okay, so let's go back now and talk about, I think the next thing up was bounds. Yes, so bounds on zeros. And this one's going to look a little bit mean. I'll warn you ahead of time. But it's useful for, especially for the graphing calculator. I don't know if you remember, but we were having some trouble, right, with our window in the last section. And if we had this rule for bounds on zeros, it would have been easier for us. So basically, be careful. Your leading coefficient here has to be 1. All right. So you may have to factor out a number. If you had 5x squared or something as your leading term, you'd have to factor out the 5. All right. But this gives us a bound on the real zeros. So, ready? It's the maximum of, so it'll be the smaller of these two expressions, which look kind of mean. So the first expression is the maximum of 1, or the sum of the absolute values of all the coefficients except for the leading coefficient. So the absolute value of A0 plus the absolute value of A1, all the way until you hit the absolute value of A sub n minus 1. So that's the first expression. The second one is, or 1 plus the max of the list of all of these terms. So instead of adding them together, they're a list. in absolute value form. Okay? So, and just a little note on the notation, the max of something means choose the largest entry in here. Okay, so let's do an example. So find a bound to the zeros of each of these functions and use the bounds to obtain a complete graph of the function. So let's just figure out what we have. A0 is 4. Oh, actually, I almost messed up. We have to rewrite this guy as with 3 factored out so that we have 1x cubed. And so if I factored out the 3, do you see I'll have 2/3 x squared and then plus 1/3 x plus 4/3. I just factored out a 3. So A0 is going to be 4/3. A1 is 1/3. A2, which is our A sub n minus 1, is negative 2/3. Okay? So the maximum of 1 and then the sum of the absolute values would be the absolute value of 4/3 plus the absolute value of 1/3 plus the absolute value of negative 2/3. So let's see what we get. That's the max of 1 or, so all of these would go positive. So 4/3 plus 1/3 plus 2/3 is 7/3. So the maximum of 1 and 7/3 is going to be 7/3. Now we have to do that other expression. So 1 plus the maximum of the list of the absolute values of those terms. So 4/3, 1/3, negative 2/3, all in absolute value, is 1 plus. So the maximum is going to be 4/3. And so when I add 1 to that, I get 7/3. So all the real zeros are going to fall between. The bound is 7/3. So all real zeros fall between negative 7/3 and positive 7/3. So when we do our graph, we know that we have to make sure our graph includes those values. So if I go here and go to my graph and go to y equals, and then I'll just clear it out. So we have 3 times x cubed minus 2 times x squared plus x plus 4. And if we go to zoom, I'm going to do zoom standard for the moment. And so basically I could be secure even if I went from, let's see, 7/3 is like what, 2 2/3. So if I wanted to, I could do my window between negative, let's see what happens if we do negative 7/3 and 7/3. Actually, you know what? That's getting too specific. If we did it between negative 3 and 3, we could be certain that our real zeros were in between that because of this bound. Okay, so this is 3 and negative 3, and this is negative 10 to 10. This was our f at x, and this is x. And we'd be done with our graph. We could be sure our graphing calculator showed us all the zeros. All right, so part B. So again, we do not have a coefficient of 1 in front of the leading, or as the coefficient of the leading term is 4. So that is not 1. So we have to factor out a 4. So we'll get x to the 4th minus, that'll be 3x cubed plus 27/4 x squared minus, I'm just going to leave it as 54/4 because we'll be adding, and then plus 81/4. So a0 is 81/4, a1 is negative 54/4, a2 is 27/4, and then a3 is negative 3. So the maximum of 1 and the sum of the absolute values of these will be absolute 81/4 plus absolute negative 54/4 plus absolute value of 27/4 and plus the absolute value of negative 3 will give us the maximum of 1 or, so let's see, 81/4 plus 54/4 plus 27/4 plus 3 will give us, let's see, 135/4 from the first two, 162/4 for the second, adding the second one. Actually, been a long week. Let's just go ahead and do it on the calculator here. So we're going to quit out of the graph momentarily. All right, so 81/4 plus 54/4 plus 27/4 plus 3. It'll give us a decimal. So if you go to math and then enter, it'll turn it to your answer to a fraction. So we get 87/2. And the max of those two is indeed 87/2. So now let's take a look at the 1 plus the maximum of the list of the absolute values. And if you take a look at that, the largest of these would end up being 81/4, so that'd be 1 plus 81/4, which is 85/4. And the smaller of these two numbers is going to be the 85/4. So the real zeros of f lie between negative 85/4 and positive 85/4, which is roughly, what, 21 and change, right? So when we do our picture of our graph, we're going to have to do, let's just figure out for sure, let's figure out for sure what 85/4 is. 21 1/4. So if we do our bounds, our bounds on our x between, what did I say again? 21 1/4. So plus or minus 22, we'll see the whole graph. So negative 22 to positive 22, and then we'll see what we have to do for our y. So let's see, our graph was, I'm going to go to second insert. I'll work with this. So we'll have 4 times x raised to the 4th minus 12 x cubed plus 27, so plus 27 x squared, and then minus 54x plus 81. And then we'll graph it. And that's not very illuminating. So let's go to our window. We're probably going to need to make this guy bigger. So let's do our window on the y values. Let's do negative, I don't know, 100 to 100. Let's see what we get. Well, we're getting there. So now it looks like we don't need any negatives. So go to our window. We don't need negatives for our y values. So let's just do 0. And let's go up further to maybe 200 just to see. And then we can increase the scale to 10 maybe for the y. And there we go. There's our graph. So we can be sure that we found that we can be sure there's no real zeros because of these bounds. So we could say right off, hey, there's no real zeros here because this graph is sitting above the x-axis, and I've graphed it in the bounds set by this theorem. So we went from negative 22 to 22. This is x. This is f at x. And then this went from 0 to 200. Okay? All right. So now the intermediate value theorem. The intermediate value theorem can tell us if there's a real zero. You're going to learn something. This is kind of a precursor to learning the mean value theorem in calculus. So so make sure you can understand this a bit so that you understand those theorems when you're in Calc 1. Okay, so let f denote a continuous function. So if a is less than b, and if f at a and f at b are of opposite sign, then what has to be true? F has to have at least one zero between a and b. So on this one, use the intermediate value theorem to show that this function has a zero on the closed interval from 1.7 to 1.8. So we know that it'll be continuous because it's a polynomial. Polynomials are smooth and continuous on their domain. And So now what we need to do is we need to find out what the signs are. So if we evaluate f at 1.7, we're going to have, let's go ahead and we'll do it on the graph. So if we go to y equals, let's just clear this all out. So we'll have x to the 5th minus 3 times x to the 4th minus 2 times x cubed plus 6 times x squared plus x plus 2, and then let's just try zoom standard and see what it turns out like. All right, kind of a groovy looking graph there. So now if you go to second calculate value, you can just plug in 1.7 and you'll find out what that function value is. So this is 0.35627, which is greater than 0. It's positive. And let's see what f at 1.8 is. So coming back to our graph, I'm just going to enter in 1.8, enter. And you see that we get a negative. So this is negative 1.02112. 0.02112, which is less than 0. So that means there has to be a 0 in between 1.7 and 1.8. So let's find it. So we'll go to second, calculate 0, and we are interested in, oh yeah, we'll be good. So here is our left bound. Here's our right bound. And at approximately, we're supposed to round to the nearest hundredth. So let's just copy this. So what we found is, so this is 10, 10, negative 10, negative 10, and then this is f at x and x. So we found right here, there's a real 0. So at x is approximately 1.73, there's a real 0. And that 1.73 is in between 1.7 and 1.8. And we're done. All right. So let's see, what do we have left to do? So we have part B on this one. So the instructions for this one were to find the real zeros of f and write this function in factored form. So just a reminder, factoring by grouping. Always double check to see if, so that you don't have to do all that dividing and all that work. Why don't you see if it'll factor? So you do A times C for your overall product because this is quadratic in form. So A times C is negative 16. 4 times negative 4 is negative 16. You're looking for something that's got a difference of positive 15. When you combine like terms, they'll be opposing signs, so it's really kind of a difference. So what two numbers make that true? You see that if you have negative 1 and positive 16, that'll work. So let's see what we got. So this f at x is equal to 4x to the 4th minus 1x squared, because we have x squareds as our middle term. We're just breaking up 15x squared into negative 1x squared plus 16x squared, and then minus 4. So you look two at a time to factor by grouping. So I'm looking at this group here and this group here. So what I can factor out of the red group is x squared, and I'm left with 4x squared minus 1. So that's the red group. What can I factor out of the green group? Good, a plus 4, and I'll be left with 4x squared minus 1. So now I can factor out the binomial 4x squared minus 1, and I get 4x squared minus 1 times x squared plus 4. Now 4x squared minus 1 is a difference of two squares, so this will factor as 2x plus 1 times 2x minus 1 times x squared plus 4, which is prime. So look at that. Just using skills from intermediate algebra, you were able to write this in factored form. So here's the factored form. And from that factored form, we can find the zeros. So 2x plus 1 is 0, or 2x minus 1 is 0, or x squared plus 4 is 0. Remember, we're looking for real zeros. So 2x would be negative 1, x would be negative a half, or 2x would be positive 1, and x would be positive a half, or x squared would be negative 4, and this is imaginary, so it will not be a real zero. Right? So the real zeros are negative 1/2 and 1/2. Oops. Okay? All right, so now we're going up to straight up problem solving, or just finding the zeros, solving this equation. And we're going to use, the skills that we've learned to solve them. So first thing to figure out, what are the max number of zeros? So max number of zeros is, good, 3. So secondly, we need to figure out the possibilities, right? So possibilities for P, possibilities for Q. So P is a factor of the constant term, which is 8. So we'd have plus or minus 1, plus or minus 2, plus or minus 4, or plus or minus 8. And then the leading coefficient is 2, so that'll be plus or minus 1 or plus or minus 2. So the possibilities for P over Q without repeating are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. So I went through for the possibilities for P and divided by plus or minus 1. Now if I go through the possibilities for P and divide by plus or minus 2, I will get plus or minus 1/2. But do you see 2 over 2 is 1, 4, which we have. 4 over 2 is 2, which we have. 8 over 2 is 4, which we already have. So we're good. These are all the possibilities. So now, doing a graph to see which ones will work out, which one we should try. So let's go to y equals, and we'll clear it out. So 2 times x cubed minus 11 times x squared plus 10 times x plus 8. All right, so I'm looking over here and it looks to me like it might go through, is that positive 2? It looks to me like positive 2 might work out. I'm looking over here. And you know if it works out, of course, by when you divide, if you get a 0 remainder, you know it worked out. So here, I'm looking here at, we're in a standard scale. And I'm looking right here that this might be a 0, right? So dividing, I'll just go up here. So we're going to divide by 2. So the coefficients are 2, negative 11, 10, and 8. So 2 times 2 is 4. Negative 11 plus 4 is negative 7. Negative 7 times 2 is negative 14. Adding those two, I get negative 4. Multiplying, I get negative 8, so I have a 0 remainder. So remember that translates, I had a cubic equation, so that gives us 2x squared minus 7x minus 4. So let's see what we got. F at x equals 2, or actually we have an equation, my bad. So what do we have? We have 0 is 2x cubed minus 11x squared plus 10x plus 8. So 0 equals x minus 2 times 2x squared minus 7x minus 4. 0 is x minus 2. And then I'm looking to see if I can factor this other guy. So overall product is negative 8. They need to combine to be negative 7. The two numbers that make that happen are negative 8 and positive 1. So I'm going to factor by grouping. So we will have 2x squared minus 8x plus 1x minus 4. So 0 is x minus 2. And then factoring out a 2x from the first two terms, I'll have x minus 4. So this is like our red group. And then we'll have our green group coming up. And what can we factor from the green group? Just a plus 1 times x minus 4. So we have a common factor of x minus 4. So 0 is x minus 2 times x minus 4 times 2x plus 1. So we have this in factored form using the 0 product property. We have x minus 2 is 0, or x minus 4 is 0, or 2x plus 1 is 0. And we get x is 2, or x is 4. This one would give us 2x is negative 1, or x is negative 1/2. So the real zeros are negative 1/2, 2, and 4. And actually, you don't need to say real zeros on this one. It actually asks you to find the real solutions. So these are the real solutions. Real solutions. Okay, part B. Here we go. So we will have the max number of zeros are good 4, because we have a 4th degree equation. polynomial equation. So possibilities for P, possibilities for Q. So P is a factor of the constant term, so plus or minus 1, plus or minus 3, or plus or minus 9. And then for Q is a factor of the leading coefficient, we have plus or minus 1. So the possibilities for P over Q are plus or minus 1, plus or minus 3, or plus or minus 9. So, graphing so we have x to the fourth minus 2x cubed plus 10x squared minus 18 times x plus 9. So when I look at this one, it looks to me like x equal to 1 is a possibility here. As this is x, y, the scale is the standard viewing window. And so this is here at x is 1. So let's do it. So I'll come over to the side here. Oh, it's not cooperating with me today, huh? Here we are. So 1 goes in the box, then we've got 1, negative 2, 10, negative 18, and 9. So we'll have 1 times 1 is 1, then we'll get negative 1 here. And we get a 0 remainder. So remember, this ended up being decreasing the degree by 1. We would get 1x cubed minus 1x squared plus 9x minus 9. So from this equation where we had x to the fourth minus 2x cubed plus 10x squared minus 18x plus 9 equal to 0. This factors as x minus 1 times x cubed minus x squared plus 9x minus 9, which I think we can factor by grouping. So x minus 1, if we factor out an x squared from the first two terms, we get x minus 1, and then a 9 from the second two terms, we get 9 times quantity x minus 1. So this is like the red group, this is the green group, and this is all still equal to 0. So the factored form would be x minus 1 times another factor of x minus 1 times x squared plus 9 is 0. So we have x minus 1, the quantity squared, so we have a solution of x equal to 1 with multiplicity 2, and times x squared plus 9 is equal to 0. So x minus 1 squared is equal to 0, or x squared plus 9 is equal to 0. So here, if you square root both sides, you would get x minus 1 is plus or minus 0, which is just 0, and x would equal to 1. And over here, x squared is negative 9. This is imaginary. We're looking for real solutions, so we're not going to worry about that right now. So the real solution is x equal to 1. Okay? All right, so here we go, a couple of applications. Find k such that f at x equal to x to the fourth minus kx cubed plus kx squared plus 1 has the factor x plus 2. So here we go. For x plus 2 to be a factor, remember x plus 2 is x minus negative 2, so c would be negative 2. And f at c would have to be 0. So that means that f at negative 2 is 0. So if I let f at x be 0 and plug in negative 2 where I see an x, I'll be able to start solving this guy. So then we'll have 0 is 16 minus k times negative 8 plus k times 4 plus 1. So 0 is 16 and 1 is 17. And then we'll have plus 8k plus 4k. So 0 is 17 plus 12k. So negative 12k is equal to 17, and dividing both sides by negative 12, k is negative 17 twelfths. Which doesn't look nearly as bad as we thought this one would be, right? So that is the answer, my friends. Okay, so what is the length of the edge of a cube if its volume could be doubled by an increase of 6 centimeters in one edge, 12 centimeters in a second edge, and a decrease of 4 centimeters in the third edge? So a cube, remember, a cube has the length equal to the width equal to the height. All right, so if we let x be the measure of an edge, then the original volume would be x cubed, right? So if you double x cubed, you get 2x cubed, right? So 2x cubed represents the doubled volume. And then increase of 6 centimeters on one edge, so that would be x plus 6 is an increase of 6. An increase of 12 would be x plus 12. And a decrease of 4 would be x minus 4. So now we crunch everything out. So if I multiply x plus 6 times x plus 12, I get x squared plus 12x plus 6x plus 72 times x minus 4. So 2x cubed is x squared plus 18x plus 72 times x minus 4. So multiplying these through, we will have x cubed minus 4x squared, and then plus 18x squared minus 72x and then 72, so that was our 18x through those last two, and then we'll have plus 72x and then minus 288. So 2x cubed equals, so the 72x is 0 out, so we'll get x cubed plus 14x squared minus 288. And then if I bring them all over to the left side, I'll have 1x cubed when I subtract x cubed from 2x cubed minus 14x squared minus 288 is equal to 0. Oops. Okay, so with this one, I mean, it's gonna it's gonna be kind of crazy to do the whole P over Q thing. I'm just gonna start. You certainly can. The reason I'm hesitating is the factors of 288. So if you factor 288, you know, that would be what? 2 times 144. So you have one factor there. 2 times 72, 2 times 36, 2 times 18, maybe it's not so bad, 2 times 9, and then 3 times 3. So you get your factors there. So I'm thinking that any combination of these might work for our possibilities. So let's just try 6, because you need a big enough number where you're going to get up to 288 in order to potentially zero out that 288 to get a 0 remainder. So I'm just going to try that. So we're going to try dividing, having a solution of x is 6. So don't forget to put in the 0 term, which is the coefficient to the x. And let's see if this works. So bringing down the 1 times 6 is 6. We'll get a negative 8 here. Negative 8 times 6 is negative 48. And negative 48 times 6, oh, we got lucky, is 0 remainder. So 6 is a factor. So that means x minus 6 times, so that'll be x squared minus 8x minus 48 is 0. Now this factors as x minus 6 times. So 48, you can get 48, 6 and 8 don't work because of the negative 8x, but 12 and 4 are going to work out. So if we have minus 12 and plus 4, you'll get the numbers that you need, and that's all equal to 0. So x minus 6 is 0, or x plus 4 is 0, or x minus 12 is 0. So x is 6, or x is negative 4, or x is 12. The negative, you don't want a negative length on a measurement there. So you would get an answer of either 6, it was centimeters, I think, centimeters, or 12 centimeters is the answer. All right? And guess what? That wraps it up for today. We'll be dealing with complex zeros on the next section. Have a fabulous day.